All right, so good morning, everyone. So this morning, we will learn the most recent experimental result and the theoretical progress on the strong interactions in hadron physics and heavy ion physics program. So, okay, let's get started, the morning session. So first speaker is the Dr. Piala Cheyenne. She will talk about the lattice QCD for high energy physics.
Thank you very much. It is a delight to be here. I'm going to highlight some of the recent results from the lattice QCD community for high energy physics. And of course, lattice QCD, by allowing us to calculate non-perturbative QCD matrix elements, can have input into a really broad range of experimental programs in high energy physics. And I'm going to touch on most of these throughout the talk today. What I want to emphasize before I start is that we're really now entering the era of precision lattice QCD for simple systems. And the definition of simple is evolving all of the time. So for single hadron matrix elements and for meson systems and beginning to be baryon systems, we really have now multiple lattice QCD collaborations with completely controlled systematic uncertainties at the level of few percent or even sub% precision. What we're also now just starting to achieve is the beginning of the era of precision or accurate lattice QCD results for nuclear matrix elements. So this is something that you'll see a lot more of in the next couple of years. And of course, nuclear matrix elements are particularly relevant for any experiment which uses nuclear targets. We're understanding the QCD effects in the fact that the target is not just a collection of nucleons, but in fact a nucleus, is extremely important. So a couple of slides introducing lattice QCD, which is, of course, a numerical first principles approach to solving the equations of QCD on a discretized four-dimensional space-time. Essentially, what we do is discretize the equations of QCD and then solve them using Monte Carlo and important sampling techniques on our discrete spacetime. So these are extremely computationally demanding calculations, so we run on supercomputers and dedicated clusters, and of course one calculation is not enough. To recover QCD, you have to take all of the relevant limits, the infinite volume limit, the limit of infinitesimal lattice spacing, and so on. In the past, and still now for calculations that are really at the edge, such as nuclear physics calculations, larger than physical values of the quark masses have also been used, although as I'll show, many calculations are now at the physical point. That's because it's computationally cheaper. You have to do a lot of matrix inversions of very large matrices that get closer to being singular as the quark mass gets lighter. So historically, this has been a cost-saving mechanism, and in that case, you also have to do the extrapolation to the physical quark masses. I just want to emphasize that this really does give you a systematically controllable and improvable approach to QCD. The input, so the lattice QCD action, has the same free parameters as QCD itself. That's the quark masses and that's alpha S. So once you've fixed those bare parameters by matching to a small number of experimentally measured quantities, such as meson masses for the quark masses, and one extra experimental input to fix the lattice spacing in physical units or to fix the strong coupling, then everything else that you can calculate, all the way up to nuclear physics quantities, are predictions from QCD. So here's the outline, and as I said, I'm going to try to touch on most of the major areas that lattice QCD has input into in high energy physics in the next 25 minutes or so. Starting with an update on values of the quark masses and alpha S from lattice QCD. So, of course, the quark masses and alpha S are the fundamental QCD parameters, but knowing them is also extremely important for precision tests of the standard model, such as at the Large Hadron Collider or at a future ILC. And if we have, for example, an ILC looking to measure Higgs partial widths to sub% precision, to see any deviations from the standard model at that level, we need commensurate control of the theory. So we also need to know the theory at sub% precision. At the moment, the largest uncertainties are in the charm and bottom quark masses and in alpha S, in the theoretical calculations. So in 2014, Lepage, McKenzie, and Peskin sort of outlined the precision goals on these quantities for ILC-type targets, and they also outlined a timeline for lattice QCD progress. So what we've had since ICHEP 2016, and I'll show some more results in the next few slides, is continued progress towards those goals, so that we're now essentially at the point of reaching those ILC precision goals. Beyond the results that I'll show, the next goals are really looking to achieve correlated determinations of MC and B and alpha S, since some of the largest uncertainties at the moment in the heavy quark masses are the parametric uncertainty in alpha. So being able to determine those in a correlated way will be very helpful. And also including dynamical QED in the calculations will help to eliminate some of the systematic effects. So here's an update from alpha S. The plot on the left-hand side of the slide is taken from the April 2016 PDG, but I've added a line here showing an exciting lattice QCD result from the last few years that I want to highlight, which is a new lattice QCD determination of alpha S based on a completely different approach than the other precise lattice QCD determinations of alpha S. So this is still lattice QCD, but it has completely different systematics. So the fact that this new result is precise at the same sort of 0.6, 0.7% precision level, which is essentially the ILC goals, and consistent with the previous best lattice QCD calculation for this quantity is extremely important. So we now have different determinations at the same level of precision, which is essentially twice as good as the non-lattice world average, with different systematic effects. So this is becoming extremely reliable from lattice QCD. For the quark masses, there's also been some exciting work in just the last year. Actually, this is from just a few months ago. What I'm showing here is the top panels are lattice QCD, the yellow and non-lattice results for here's the charm quark, the bottom quark masses, and some of the light quark masses. So the highlight here is this result right at the top. So you see there have been significant improvements in the heavy quark mass determinations from lattice QCD in just the last couple of years. This is using a new method based on heavy quark effective theory. And again, comparing the precision of these results to the ILC goals from that 2014 paper, we're now reaching very close to those precision goals from lattice QCD with completely controlled uncertainties. Some of the largest uncertainties, particularly in the heavy quark calculations here, are the discretization extrapolation, so this will improve further with including more lattice spacings. Okay, so to now give a brief review of flavor physics. So again, what lattice QCD can provide are really hadronic matrix elements. So when we're talking about, for example, flavor physics calculations, we have this sort of a setup here where things that you can measure experimentally, decay rates, branching fractions, are related to those hadronic matrix elements via some known things and some CKM matrix elements. So there's really two main efforts in using these hadronic matrix elements for flavor physics. The first is to input this side and try to extract the CKM matrix elements in the middle. So this, of course, requires experimental input. So what's done is to use simple sort of tree-level decays where you expect no significant new physics contribution, and then combine those with hadronic matrix elements to extract the CKM matrix elements to high precision. So lattice QCD really can access essentially all of the CKM matrix elements to high precision now from these simple processes, where simple is one hadron in the initial state and one or two in the final state. I'm going to focus mostly on talking about some of these second types of calculations where what's done is the CKM matrices are input and the hadronic matrix elements to get a QCD prediction for a rare decay that we want to compare with experiment on the left-hand side here. So of course here the goal is to target processes that are sensitive in particular to beyond the standard model physics and set a standard model benchmark to compare experiments to. So just before I do that, I want to sort of advertise and highlight the FLAG Flavor Lattice Averaging Group, which is a community project including members from most major lattice QCD collaborations that aims to do for lattice QCD what the PDG has done. So by providing an evaluation and grading of different lattice QCD calculations for non-experts and then averages of the best results as lattice community consensus values. So here are some references. The December 2017 update is online. What's really exciting is that a new version of this report is planned for 2019 and that this will be the first version to begin to include baryon quantities, so things like the axial charge. So this is really a sign of what I said at the start of the talk, that the scope of lattice QCD to do controlled precision calculations is expanding. And so it's expanding to include baryon quantities at the level where including them in these reports makes sense. So here's just an example of what you'll see in one of these FLAG reports. So decay constants, form factors, mixing parameters, also the quark masses that I showed before, are summarized in tables where calculations are sort of color-coded. Red doesn't meet the requirements considered for including in an average. Open green also hasn't been included in the averages for other reasons, and then the solid green are the ones included, and then average values are quoted from different collaborations that are judged to have all systematics under control. This is just an example. For these particular quantities, there have been also new results that are not yet in flag that I've noted here. So to come to an example of some exciting results in the last few years of lattice QCD for flavor physics, looking at the beta D L nu and beta D star L nu decays, there have been new lattice QCD results that show a 4 sigma tension with experimental measurements for these rare decays. So BEL2 will provide further experimental constraints, and of course the lattice QCD calculations will improve. What we're looking at here is really this difference between the red ellipse from experiment and this little blue ellipse from theory. So in the horizontal direction, this ellipse is constrained from lattice QCD calculations from several collaborations. In the vertical direction, there are no lattice QCD results yet. At the moment, the standard model prediction uses some experimental results plus heavy quark effective theory at the charm mass scale, so that may have some systematic uncertainties that are difficult to control. So what's very exciting is that in the last few years, there's been a lot of progress on lattice determinations of the beta D star LNU processes as well, which will provide also direct lattice QCD input for this direction in this point here and further constrain those uncertainties. So the second thing that I want to highlight, which is really looking towards the future in the next few years, is the K plus to pi plus nu bar. So this is, of course, a rare decay process that's sensitive to many different new physics scenarios. And there's a number of experiments. Well, there's the NA62 experiment in particular, which had one event in 2016 and is looking to be able to test the Standard Model at something like 10% precision in the next few years. From lattice QCD, a highlight of the last year is that there have been exploratory calculations that demonstrate the feasibility of calculating this from lattice QCD. So these are not yet at the level of fully controlled uncertainties, but the authors say that in the next 4 years or so, a fully controlled calculation will be possible. So this is particularly significant because it also includes the long distance contributions. So this decay has several different contributions, short distance pieces, which are pretty well constrained using perturbation theory, with the only non-perturbative input you need being the semi-leptonic kaon decay form factors, which are reasonably well known. But the long distance piece, which is estimated from phenomenology to be something like 5%, is much harder to constrain. But this lattice calculation very recently, just last month, includes these long distance pieces and shows that it will be possible to do this calculation from lattice QCD. So that's something very exciting to look forward to in the next few years. Okay, so moving on to G-2 highlights. Of course, with G-2, the very exciting thing is that there's this discrepancy between measured values for the anomalous magnetic moment of the muon and the standard model estimate. So the difference between this yellow band from theory and this blue point from experiment. And of course, we all want to know whether that's a sign of new physics. Over the next few years, experiments are looking at a 4-fold reduction of uncertainties. So the E989 experiment's already started taking data. I believe the E34 experiment at JPark is a little bit later in schedule, around 2020. And so if there's no shift in the central values with commensurate theory improvement, we'd be looking at something like a 7 standard deviation discrepancy here. The key part of that sentence was the commensurate theory improvement. Of course, that's essential to really be able to make this comparison. So recently, the muon G-2 theory initiative was formed. Here's a link to the website, and that's looking at putting out a report at the end of this year, summarizing the community status for G-2. So I just want to highlight a couple of exciting lattice QCD results on this front. So firstly, just to break down the standard model contributions to muon G-2. There's QED effects, electroweak effects, which are constrained extremely well and known to very high precision. What's known far less well is hadronic effects. Those are the major uncertainties: hadronic vacuum polarization and hadronic light by light. So these are the dominant uncertainties, and they're also those which are calculable in principle from lattice QCD. So just some highlights for hadronic vacuum polarization this year has seen the first lattice QCD calculation, including QED, including isospin breaking. So really pinning down all of those systematic uncertainties in the calculation from lattice QCD. And I'll highlight that a little bit further on the next slide. For hadronic light by light, which I don't have a lot of time to talk about in detail, there's also been some progress since ICHEP 2016, further constraining systematic uncertainties. But I want to focus in particular on the hadronic vacuum polarization, where just this year a paper came out showing that now the most precise way of constraining that from the standard model is to combine experimental data with lattice QCD. Lattice QCD on its own, these green points, still have significant uncertainty compared with what you can get from R ratio data that's involving E plus E minus to hadron experimental data. But what's been shown is that if you combine lattice with experiment, you can get a much more precise result, this yellow point, or somewhat more precise result. So how that's done is by separating out this contribution to AMU, the hadronic vacuum polarization piece, into different distance scales. So C here is a correlation function. These here are vector current insertions. So by separating out into different distance scales here, the R ratio determination is here in purple, and lattice QCD is in blue. So you see that most of the uncertainty comes here from poor determinations at long scales. There is a range, however, where lattice QCD is more precise than experiment. And so by combining the two over this range, which is then integrated over to give this contribution, you can achieve more precise determinations. And of course, lattice QCD, while this range is going to be difficult for a while, will continue to improve in this window. And so improving the determination that way is on the horizon for the next few years. So parton distribution functions, which of course are, again, fundamental quantities that we'd really like to know, fundamental aspects of hadron structure, and also, again, are needed in searches for new physics, for example, at the LHC, through top quark and Higgs boson coupling measurements. Historically, lattice QCD has only been able to provide moments. So those are x-weighted integrals, where x is the longitudinal momentum fraction over the parton distribution function, so this tower. But what's been shown in the last few years is that including these constraints in global fits can reduce uncertainties. So here are some examples to a community white paper, and I'll also show an example in the next few slides, and also show some examples of some of the control we've been able to achieve of lowest moments in the last few years. And finally, I'll just mention that we're now at the level of being able to actually do first calculation of the x-dependence of PDFs from lattice QCD, and I'll show some of those early results. So moments of the PDFs. From lattice QCD, we can calculate the lowest moments most cleanly, although there's efforts now to go beyond that. This difficulty comes from the breaking of the rotational symmetry group to the hypercubic group and mixings that induces. But at this stage, for low moments, state-of-the-art calculations have fully controlled systematic uncertainties, in some cases competitive or better than experiment. So here's an example from 2017, where all terms of the nucleon momentum decomposition have been calculated with controlled uncertainties. So that's the up quark, down quark, strange quark, gluon piece, all calculated separately at the physical point with systematics controlled, and the total sums to 1 within uncertainties as it must. So that's really an achievement for lattice QCD of these moments. As you'll note, what's really fairly straightforward on the lattice is doing the flavor separation, separating the light quark pieces, the strange quark pieces, and the gluon pieces. So this is really something also for the PDFs where we can provide valuable input to experiment. So here's an example showing how including these moments in global PDF fits can improve constraints. Here I'm showing an example for the transversity PDFs and the Collins fragmentation functions, which are also sensitive to transversity. And the difference with only semi-inclusive deep inelastic scattering data, which is the yellow broad band up to the grey band, is the range of direct constraints from that. And then the difference to including just the tensor charge, so the 0th moment of this transversity PDF, the difference that makes in the global fits. So doing this is now a community project. Here's a reference, and also on the previous slide, to a community white paper. Also, the x-dependence of parton distribution functions, we're now at the stage of the very first calculations. So of course, light cone quantities are difficult to calculate in Euclidean space. So what's done is essentially you have to rotate off the light cone and then take a large momentum limit to come back onto the light cone, which has many systematic uncertainties, particularly in the taking of that large momentum limit. So having really better constrained results from an experiment is a long way off, but this is extremely exciting, and what we've seen in the last few years is progress to the point where the lattice QCD in blue is consistent with, for example, the CT14 phenomenological PDF fits. So this is, again, a space to watch in the next few years. There's been extremely rapid improvement even since ICHEP 2016. Okay, coming to neutrino physics, where, of course, experiments that we've heard a lot about at this conference, long baseline neutrino experiments, are seeking to determine the mass hierarchy, mixing parameters, and so on. For example, for Dune, to differentiate between different mixing and CP parameter scenarios, you'd need an energy reconstruction of the neutrino energy from the final state to something like 100 MeV, which is extremely challenging and requires really solid knowledge of the nucleon and nuclear level amplitudes here. Lattice QCD can provide direct non-perturbative QCD matrix elements, which in this particular energy region of about 1 to 10 GeV, which is where the energy distribution peaks for long baseline neutrino experiments, it's a very complicated region, quasi-elastic, deep elastic scattering, resonance effects, and so on. Lattice QCD can provide useful input in most of these regions. I don't have time to talk about them all. I'm just going to highlight some results for the quasi-elastic region, so in particular the axial and pseudoscalar form factors. So nucleon properties and hadron properties in general are, of course, historically difficult calculations for lattice QCD. But what we've seen over the last few years, here are two different collaborations from 2017, that we have lattice results with controlled uncertainties for particularly the Q-squared dependence of, for example, the axial form factor. So here the blue and orange are lattice QCD results. These bands are from different experimental determinations. Here this black data is from experiment. So you have to remember the lattice data is correlated, but the Q-squared dependence constraints are really now reaching the point of being competitive with experiment. And what should be noted is that dipole parameterizations don't really fit very well, so what's being used are model-independent Z parameter expansions and things like this at this level of precision. Again, flavor separation is something that we can do effectively from lattice QCD, so things like the strange quark contributions to the actual form factors have also been determined and can be separated cleanly. And the pseudoscalar form factors, we're now also just seeing the first calculations with controlled uncertainties of those in the last few years. And a particularly interesting thing to note here is deviations from the pion pole dominance ansatz, which is, of course, often used to relate the pseudoscalar form factors to the axial form factors in models. So what we're seeing, the difference between the blue and the white points here, or the deviation of these points from the horizontal line, is showing the deviation from that pion pole dominance ansatz at low Q squared. So we're really clearly resolving that this is not very good at low Q squared. So those are the exciting results from the last couple of years here. So finally, coming to dark matter, where, of course, we would love to see dark matter directly in our direct detection experiments, where we're looking for weakly interacting massive particles to interact and collide with nuclei in our detectors. The detection rate, of course, depends on dark matter properties and also on the probability of the interaction with the nucleus. So I emphasize nucleus. For example, in xenon 1-ton or n-ton detectors, you have xenon nuclei, not protons. So nuclear effects are extremely important here. So I'm going to show an example in the next few slides. Given that the low energy limit of a generic spin-independent interaction is scalar, we of course talk often about the scalar matrix elements as being relevant to set theory constraints or to interpret a detection if we have one. What we can do from lattice QCD is to determine nucleon and really at the beginnings of being able to determine nuclear matrix elements. Of course, other sorts of interaction can also be constrained, but I don't have time to talk about them. So for the scalar matrix elements of the nucleon, there's been a long evolution of the last 20 or so years, particularly for the strange scalar matrix element, now converging to reasonably precise results for both the light and strange scalar matrix elements from lattice QCD. This is time ordered. This is 20 years ago and this is now. The light quark is now beginning to be competitive with phenomenological estimates, and it should be noted there's actually some interesting tensions with the latest lattice results with some extractions using Roy-Steiner equations. The strange quark scalar matrix elements or the strange quark sigma terms are much more precise than can be determined from experiments. So this is really where lattice QCD provides very important input. Although, as I said, of course, in something like a dark matter direct detection experiment where you have very large nuclei, nuclear effects are potentially extremely important. The Born approximation is that your dark matter interacts only with single nucleons in your nucleus. So then the nucleon scalar matrix elements that I showed on the last slide are what you need. Of course, you might also suspect that you might have interactions that are non-trivial with multiple nucleons, that 2-body, 3-body, 4-body effects might be significant. So I'm happy to show here some of my own work recently, trying to calculate the scalar matrix elements of light nuclei to determine these 2-body, 3-body, 4-body type effects. So these calculations, unlike all of the others that I've showed in this talk, which have controlled uncertainties, systematic uncertainties in every way, these ones don't yet. In particular, my quark masses are large, the pion mass is around 800 MeV for these particular calculations that I'm showing. So this is a different world where nuclei are bound a little bit more deeply than they are in nature. But what you see here is 10% nuclear effect. So that is taking the difference between what you'd get multiplying up nucleon matrix elements to a nucleus and comparing that to what you get doing an actual QCD calculation in a nucleus, 10% nuclear effects in light nuclei. So I said this is a different world where nuclei are bound more deeply. The reason this is really interesting is that the scalar and tensor charges see something like 1% or sub% effects. The scalar charge sees 10 times that. So if this persists, we're now doing calculations at the physical masses to try to control these systematic uncertainties. This would be something you really can't neglect when you're thinking about scaling up to, say, xenon in terms of setting limits on dark matter. So to summarize, lattice QCD is really able to, and now is, providing essential standard model input for a whole host of high energy physics experiments. And I think I managed to touch on most of these in the last 25 minutes. And like I emphasized, we're really now entering the era of precision lattice QCD for simple systems. So, and the definition of simple is really expanding. The flavor lattice averaging group is going to expand in 2019 to include some baryon structure quantities in its community summaries. And over the next few years, so certainly by ICEP 2020, many more quantities will have moved from being things that we can sort of determine but with some uncontrolled systematics to things where we have precision percent level calculations. And also, nuclear matrix elements is really something that in the next few years will be constrained very well from lattice QCD. Or, not for xenon or argon that you might want for Dune, but certainly for light nuclei, and we're working on larger nuclei. Of course, lattice QCD also provides important input for many other topics that I didn't have time to cover, from hadron spectroscopy to BSM physics, the nuclear structure, like I said, and finite temperature and density. 2 weeks from now is the annual Lattice QCD conference to be held in Michigan. The talks will be online. The proceedings will be available in a few months. Thank you.
Okay, thanks, Piala, for this comprehensive review on the lattice QCD. So it's time for a couple of questions. Yes.
So, do you have any news on the B sub C2 GPSI form factor? Because we are going to update the RGPSI measurement quite soon, and this would be the main or the dominating systematic uncertainty.
Okay, no, not here and not in my backup slides. But there might be something at the Lattice conference in 2 weeks, so I would keep your ear out.
Thank you for a nice talk. And all the list, you don't mention neutrinoless double beta decay. Will the lattice have anything to say about the matrix element in that problem?
Oh yes, this is actually something I've worked on myself. So of course studying double beta decay in the nuclei that actually undergo double beta decay is extremely challenging for us. But what we've done recently is look at the NN to PP transition matrix element. Of course that's not a decay that happens in nature, but it's a well-defined sub-process of the decays that do happen. We can study this on the lattice, and we've done so at larger than physical values of the quark masses. So for the neutrino full decay, what we've seen is that there's a really important non-negligible short distance contribution so that you can't absorb into, say, 2 insertions of the axial charge. We're working on bringing that down to the physical point, and also David Murphy, who gave a talk at this conference, is working on the neutrino-less part. So this is something we're actively working on. We have a couple of papers on neutrino full. I can point you to them.
All right, so one more. Okay, go ahead.
Super, thank you very much. What are the prospects for lattice calculations of nuclear PDFs?
Yeah, so actually we're working on this as well, and something that I'm working on in particular is trying to resolve, say, the EMC effect by looking at moments of nuclear PDFs at the first start, right? And these we can calculate with not quite controlled systematics at this stage, but we're working on it. Doing the X dependence, I mean, that's another whole hurdle again. That's not completely controlled in the nucleon case, but in principle, harder in the nuclear case, it's just computationally much more expensive and adds more onto the systematics uncertainties that are to control. So moments, yes, we're working on, should have controlled calculations on a 3 to 5 year time scale. X dependence, harder after nucleon X dependence, but it can happen.
Super, thank you.
Okay. Okay, one last quick question, please.
Yeah, is there any news on B sub S and BD decay constant and back factors in unquenched 2+1+1?
Yes, there was a paper just this year, I believe. And I think there's a reference to it in my backup slides if you look online, and
Okay.
if not, I can point you to it.
Okay, thank you.
All right, so let's thanks again to speakers. Looks like a very good startup. So excellent talk and excellent questions. So we will have the coffee break. So we will have some more productive discussion during the coffee break. Okay, let's move on to the next speakers. The Dr. Latifa El-Luathiri will talk about experimental aspect of the strong interactions and hadron physics.
Okay, so first I would like to thank you for the invitation. This is a great honor to be here. And it's really an exciting time for our field of research. I will show you there are some very interesting new results and also a bright future ahead. So you gave me a challenging task. It's impossible to cover all the progress that has been made in hadron physics and strong interaction for the last decade. So what I decided to do is give you complementary talk to what you have heard during this conference, during the parallel sessions and also the plenaries. So, and I will start about what we want to do and put it in the context of really the history of the universe. So at the beginning of the universe, a dramatic event happened in the first microseconds, where there was this transition from free and confined quark to confined quark forming hadrons, protons, neutrons, and other baryons. And when during this process, the elementary particles that are almost massless, they acquired mass by coupling to the gluons and also due to the chiral symmetry breaking. So, and what I'm showing here is a QCD phase diagram showing this transition between unconfined quarks and confined quarks. And this is not simple order phase transition. It's crossed over between two interacting matter phase transitions, which is believed to be mediated by nucleon excitations. And they will show you, so understanding the in-star spectrum is critical component to understanding QCD. So, and they will focus on how we do with electron machines to explore these events and unravel the mechanism really of confinement. So this is just cartoon to show you how the light quarks becomes heavy, and just an illustration if it works. Doesn't work. So it's really that, it's coming. So as we start from here, from higher energies, the higher temperature, where the quarks now becomes heavier and heavier. And this is related to where free quarks become confined. So when we do an experiment, actually we start from here with the constituent quark that are now, and we vary our energy transfer, our probe, and we should see the quarks getting smaller and smaller mass. And this is in comparison to lattice QCD and the model of the Dyson-Schrödinger equation. So few historical moments, markers before I get into the study of the structure of the protons. So what do we know about the structure of the proton and the neutron? So the first thing is that we know that we had the first measurement of the proton magnetic moment that gave us the first indication that the proton has structure. Then after that, detailed elastic scattering enabled us also to understand the proton structure. Then there was deep inelastic scattering, and there was the Nobel Prize award in 1990 to the pioneering investigation of the deep inelastic scattering. And now we're dealing now with the substructure of the proton in terms of quarks and gluon. Then in 2004, we had the Nobel Prize for the discovery of asymptotic freedom of QCD that was developed in 1970s. That now allow us to do calculation in a regime of perturbative QCD that allow us to access the internal structure of the nucleon. So what we will do with electromagnetic interaction is to probe hadron. First is to do the spectrum searching for new baryon state and meson states. We also measure form factors that will enable us to measure the charge and current densities and map the transition from soft to hard processes. Then structure functions in deep inelastic to determine the parton and spin distributions. Then the new thing that has been developed in the mid-90s is the development of generalized parton distributions and transverse momentum dependence that allow us now to go deeper and understand the 3D imaging of the quark content and orbital angular momentum. And also, in the last few years, we have development that shows that the moments of generalized parton distribution enable us actually to access the pressure and forces inside the proton. So in light blue, I highlighted what they will be examples that they will be showing. So of course, to get to the result I'm going to show, this was tremendous effort in the experimental technique aspect. Both the technology of the detectors enable us to go to higher energy, higher polarization for both target and beam, and also large acceptances and continuous beam, high luminosity. All of that has been critical, and there are experiments all around the world, from Germany to United States at Jefferson Lab, to CERN Compass, to China, to Japan. So I will talk a little bit about the laboratory I come from. This is Jefferson Lab. It's a DOE laboratory operated by the Office of Science. It is a linear accelerator. It is linear accelerator delivering beam to 3 experimental halls, hall A, B, and C, that are equipped with complementary equipment to access complementary information. And they want to really point out that we are big on education, and so far we have 1/3 of the US PhD students. So far we have about 600 PhD students that are granted and 211 that are in progress. This is how the CBAP was operating from 1995 and to 2012. Since 2008, we went through a major upgrade that just started operation, and they will talk about that in a few slides. So this is now just a few examples of the quality of the data that is coming from all the facilities that I showed you before. This is an example of, so we need large acceptance detectors, and we need to cover the full kinematical coverage in order to get the information that we want to have. And we need to have it in timely, which means that we have also to have high luminosity. And we need all combination of polarization, beam, target, transverse, and longitudinal. And we want to go from the photo production point to the high energy. So this is just to show you the quality of the statistical accuracy and systematic accuracy of this type of measurement. This is an example of photo production of K plus lambda, and you can see the different small bins and the statistical and systematic uncertainties that are almost invisible. This is from the class data at Jefferson Lab. Equally and beautifully is the pi0 cross-section that is obtained from MAMI, and you can barely see the statistical uncertainty. All this high quality, and this is just one sample. Of course, there's obtained from different beam energies and also for different final state. All of that have been essential to be combined from different laboratory to develop almost model-independent framework for partial analysis to develop the N-star spectrum. And if we want to, this is actually tremendous progress since 2012. So if we look at the particle data group from 2012 and we compare it to 2018, what the stars means is areas where we didn't have anything. This is discovery of new state. And when we have, here we had one star which is poorly known state, and here is very likely and well-defined state. And you can see the progress that has been made from 2012 and 2018. Obtaining an accurate account of the full nuclear resonance spectrum, sorry, I'm doing things wrong. Obtaining an accurate account of the full nuclear resonance spectrum is one of the bases for making progress in our understanding of strong QCD. And as I showed you earlier at the beginning of my introduction slide, showing the transition between the two phases. And there is actually starting collaboration between the heavy ion community doing lattice calculation and the experimentalists from the electromagnetic community working together to understand really the underlying processes for a strong QCD. So, and I want just to point out that the group from Korea has really played an important role in all this field. And there was a workshop last week that was held in Korea here, and next one will be in Jefferson Lab. The last one was initiated, and it has been in Orsay. So now to the deep inelastic scattering, there was impressive progress here also from different laboratories, CERN, SLAC, DAISY, and Jefferson Lab in the area of DIS, as well as in semi-inclusive and exclusive processes from Hermes and Jefferson Lab, polarized PP scattering, Phoenix and STAR, and polarized E plus E minus. So, but that's allowed us and put the possibility for us now to start asking the next generation of questions. So we want to understand what are the quarks and gluon and then intrinsic spin distribution in space and momentum inside the nucleon. What is the role of the orbital motion? What is the forces and the confinement forces inside the nucleon? So what we have been doing, and I like to give this analogy of how the heart works, what we have been doing with the deep inelastic scattering inclusive processes is like studying the heart in one-dimensional. And what we would like to do is understand and get to the heartbeats of the proton. And for that, we need a different technique, both from the theory and the experiments. So, and this is where it came from the development of the generalized parton distribution. So this is what I mentioned with elastic scattering. We are measuring the transverse charge and current. With the deep inelastic, we are measuring parton distribution. But now, with the new technology and development in the theory of the generalized parton distribution that I will explain in a minute, but also the capability of doing deep exclusive processes. So we're at high energy, but we're detecting all the particles in the final state. We can access to the generalized parton distributions. So, and generalized parton distribution, the formalism is really a breakthrough in the 1990s in QCD. It allows us to develop a process which is the deeply virtual Compton scattering. It can be deep exclusive processes, but DVCS is one of the cleanest one as tool to characterize the structure of the nucleon within QCD, showing how its property can be probed in experiments. And the work has been developed by Dieter Müller, Shandong Ji, and Anatoly Radushkin. So the process is the following: is based on the full win, is that hand-back diagram, sorry, that can be factorized in two parts. part that can be calculated exactly in perturbative QCD, and part that has the structure of the proton that can be parameterized in terms of generalized parton distribution. So, and when you do an experiment for the deeply virtual Compton scattering, I'm confusing this. So we detect the scattered electron and the photon and the recoil proton. So the beauty of the deeply virtual Compton scattering is that we don't destroy the proton. We are high energy enough that we interact with the parton inside the proton, but we detect the particle in the final state, including the proton. So, and first observation for the deeply virtual Compton scattering, it was observed at Hermes as well as CLASS in 2001. And that was really the initial new generation of experiments that we can measure this process, and it's compatible with the theoretical prediction. So then it triggered a series of dedicated experiments that are dedicated to study the deeply virtual Compton scattering at Jefferson Lab, both in Hall A and Hall C and Hall B. And with large acceptance, we are now able to measure all these particles in the final state, detect them together, and measure cross-section and beam spin asymmetry. And that shows you the beauty of the measurement with the CLASS detector. So now how do we go from that to the information about the internal forces and pressure inside the nucleon? And the first theory of formalism was written by Heinz Pagel in 1966, American physicist who actually wrote very nice books, or popular books on physics. And he, the first one, put the matrix, the energy momentum tensor, and talked about the mechanical structure of the proton, and connected the off-diagonal element to the pressure and to the forces. But with the statement that it was impossible to get to them because the only way to get to them is through graviton, and it's so weak that you cannot really measure it. But the fact of the development of the DVCS process and GPDs allow us to have access to this very important fundamental information. And Chandon Ji rewrote the nuclear matrix elements in 1997 and expressed it as function of these three form factors. So the mass distribution, the orbital angular momentum, and also D1. And this D1 term has both the force and pressure distribution. And this is beautiful. And now the quantities that they were only accessible through graviton, they are accessible through DVCS, where the two photons are mimicking the graviton, spin 1, mimicking the graviton of spin 2. And he rewrites this form factor, which I will call gravitational form factor, as function of GPDs. So now we have beautiful technique to have access to the pressures and forces inside the nucleon. So, and in 2003, Maxim Polyakov now correlated this D term to both the pressure and forces. So if we can do an experiment and access to the D1 term, we have access to the pressure and forces. And this is what we did. So as you saw before, GPDH is related to the D term, and D term is related to the pressure and to the forces. So, and for getting to the GPDH, we need to measure both the cross-section and the beam spin asymmetries and correlate them. And this is the first measurement of the pressure distribution of the pressure distribution as function of R. So we can see we found very repulsive forces up to 0.6 Fermi and very confining forces at largest distances that make up really the stability of the proton. And we average pressure at the center of 10 to 35 Pascal. This is in comparison to the pressure at the center of the neutron star, order of magnitude bigger. So these works open up for us new research, fundamental to have access to the gravitational form factors in the nucleon. And we have the same tool now to get to the pressure distribution. That's made lots of news all around the world, including Le Figaro in France and also in some papers even in Korea. So the next steps are really to do the same technique and use the same data to have access to the forces and to start talking and measuring the mechanical radius of the proton. When we talk about the proton, we talk about the charge radius, but here we would like to measure the mechanical properties of the proton. So next is also to understand the orbital angular momentum, which is still a puzzle, and its contribution to the spin. So that's major thing that we have to work with. And this is, again, the sum rule that I showed you before that's related to GPDs to the angular momentum, except that now I have to have GPDE that require transversely polarized targets. And also imaging. Imaging both in momentum space and in transverse space. So this is done by measuring both the semi-inclusive processes that allow us to do imaging in 3D momentum space and measuring GPDs that allow us to measure the imaging into 2D transverse coordinates and correlate it into the longitudinal momentum. So, and this is now being possible with the 12 GeV upgrade, where we upgraded the energy from 6 GeV to 12 GeV by adding 5-carat module in each LINAC and added in an additional hall for spectroscopy. So the project was completed on cost and on schedule this September 2017, and we started taking data this spring. And it even received the Secretary Energy Award. So it has now 3 halls instead of 3. So Hall D is built, new infrastructure, new hall for exploring confinement, but studying the exotic mesons. Class 12 has been upgraded and really state-of-the-art detector to continue the generalized parton distribution and semi-inclusive processes. And Hall A has new experiments that are planned in the future, and Hall C to do precision measurements for valence quark properties. So just, it was done, and we had several dedications and also visits from high officials. This is actually the visits from the Secretary of the Department of Energy. He was actually fascinated by one of our detectors that was built by our collaborators from Saclay, the micromegas, where there was just in the news that was used for the pyramid tomography, and I was talking about the proton tomography. So we work in a context of long-range plan in the United States. So there are the following recommendations. Recommendation number 1 is the completion of the 12 GeV upgrade, not just the projects, but also extracting the physics. Second is the double beta decay. And recommendation number 3 is the electron-ion collider. And there are 2 versions of the electron-ion collider that are being developed, one at Jefferson Lab Design and one at BNL. And recommendation number 4 is the incremental upgrade to the detectors. So this is electron-ion collider is really the future facility for QCD. It has been recognized in 2013 by the NSAC Subcommittee Future Facility as absolutely essential and central to understanding QCD. And there was, in the National Science Academy of Engineering and Medicine in the United States, the Division of Engineering and Physical Sciences, there was a committee that was put in place, and actually the report is ready. The report is, all the signs are going in the positive direction, and the report is ready. This week is being presented to the stakeholder, the Department of Energy, next week to the Hills and to the Office of Science, Technology, and Policy, and it will be available to the community by the end of July. So it's large international collaboration from all around the world, about 788 members, 169 institutions, and we're looking to increase our base both in Asia and also in Africa. So in summary, lobe-tone scattering is a powerful tool to probe rich internal structure of the nucleon. We have new perspective on exclusive reactions, physics that opens up a new avenue to test confinement mechanism. And now we have access to this partonic momentum tensor that enable us to get both to the forces and the confining pressure inside the proton. The three-dimensional imaging of nucleon helps solve the remaining puzzle of the proton spin and uncover rich dynamics of QCD. An exciting time is just starting with the 12 GeV era with high precision measurement that we just started taking data this spring. And of course, the electron-ion collider is the new frontier of QCD that's opened us new avenue in studying quantum chromodynamics. And thank you.
Thanks, Latifa. We have the time for one question.
So can you say a few words about the time scale, how soon this electron-ion collider can start operation? So is it next 5 years, 10 years? So when you expect?
So if this report, what we think what it is, it will trigger the CD0, which is the mission need. Then from that, you have to work out all the critical decisions of a project up to CD4. And then if I take just how it took us to get to the upper grades, you are talking about decades. Yeah, but that's really what it takes.
Any other question? So, Latifa said, very good luck with your new heavy ion collider. So I'm LHC guy, but
Sorry?
I'm LHC guy, but very good luck with your the electron ion colliders.
We're looking forward to that.
All right, so let's thanks again to the speakers. So next speaker is the Dr. Cheng Shi-Pang. So he will talk about the exotic hadrons.
Okay, so good morning. So I am Shuang Fang from the IHAB. So it's my honor to be here to present this overview talk on the exotic hadrons. So this is the outline of my talk. First, I will give a short introduction, and then I will highlight the discoveries of the exotic hadrons, including the X, Y, Z, and P states. And also, I will just present the possible theoretical interpretations for these hadrons. So we know that the birth of the quark model is really a breaking through in our understanding of the inner structure of the hadrons. In this model, and the mesons are composed of the quark and the antiquark, and the barons are composed of the three quarks. But actually, in QCD allows for the states beyond the quark model. For example, the dibion, pentaquark, tetraquark states. Actually, for a long time, we have a huge theoretical and experimental efforts to search for the exotics beyond the quark model. But we really observed many hadrons, but none convincing candidates for the exotic hadrons until 2003. I think we observed a very narrow structure, X3872. This narrow structure actually inspired the experiments to observe the many exotic hadrons, including the X, Y, Z, and P. So this is the timeline for the discovery of the exotic hadrons in recent years, and by different experiments in different processes. And at this conference, I think many present their recent results on the search for the exotic hadrons. Here, I just provide a list for these talks. So in this talk, I will just highlight some of the recent results. I'm sorry if I missed some of the results. So let's start with the X states. And to search for the B decays to the K-on and psi prime, and we observed an unexpected, and very narrow peak for the X3872. And recently after that, actually many experiments confirmed these states. And recently, I think batch 3 also observed these states using the ISR, the initial state radiation. And most recently, Atlas and the Compass both observed the structure for the X3872. Actually, this is well estimated so far, and we can see that this structure is quite close to the mass threshold on this star. So far we know this is isospin singulate, and the GPC is determined to be 1+ by the LHCb experiment. Actually, it's also we know it could be produced in different processes, even in the B decays and even in the Y4260 decays. We may discuss it later. Actually, recently, the LHCb reported the ratio of the X3872 relative to the psi prime and relative to the J psi. Theoretically, this ratio should be less than 1 if it is a molecule. But we can see that this value is about 2.5. Maybe this indicates the X3872, maybe it's not a pure molecule. Maybe it's a mixing of the Cas1 and the molecule. And of course, one may ask, how about the X3872-like state in the bottomonium states? But CMS performed the analysis. Actually, performed the analysis, we can see that besides Wolfson 2s and 3s, there is no clear pictures. In particular, for the around the B star threshold, there is quite flat. And let's come back to the B decays, because we know that the X3872 can decay into the rho J psi. Then how about the system of omega J psi? So the Bell performed this analysis and observed a clear enhancement just around the omega J psi mass threshold. And later, with a large data sample, Baba performed this analysis again. We found that actually this enhancement includes two contributions. One is the 3872, the other is the X3815. And at present, I think even in the two photon processes, both Baba and Bell observed this structure. But in the two photon process, we didn't, and the GPC from the Baba results is also determined to be the O++. But at first, we thought this is just a Chi-C2 2p state, Chi-C0 2p state. But the mass is a little bit higher than the theoretical predictions. Actually, recently, Bell found a better Chi-C0 candidate. This is the X3860. This enhancement is observed in the E ± to J psi d bar. And we can see this is a clear enhancement just around the d bar mass threshold. And its spin parity favors to the O+, and also the width and the mass consistent with the theoretical predictions for the Chi-C0. But actually, the Bell also performed analysis for the J psi D star and D star D star. We can see that clear enhancements observed. So this is the X3940 and X4160. But the interesting is we didn't observe these structures in the mass spectrum of the D bar. Okay, so yeah, after studying the omega gypsy and the rho gypsy, it's natural for us to study the phi gypsy system. So the CDF, for the first time, CDF performed this analysis, just observed the narrow and clear enhancement. And after that, D0 and CMS also performed an analysis and confirmed the existence of the X4140, but they also observed another structure just around 4.3 GeV. So, but in the two-photon process, actually, Bell didn't observe the structure, 4140, but observed another structure, X4350. So the latest result is from the LHCb. Here, this is a Dulles plot, and we can see there are some structures, and which is clear in the mass spectrum of gypsy phi. Actually, LHCb performed the amplitude analysis and found that besides these two structures, another two is also necessary to provide a good description of data. And for these two, the spin parity is just 1 plus pi plus. For the other two, is just the O plus plus. And recently, and I think it's an interesting structure is about X55 and 68. Because I think just 2 years ago, D0 observed this structure, and most recently they confirmed this structure using the both hadronic and semi-leptonic decays. But because this is interesting, so this inspired the other experiments to search for these states. Actually, the CDF, CMS, LGCB, Atlas, all these experiments try to search for these states. But so far, we can see there is no clear peaks just around the 5.5 GeV. So it's quite flat. But I think maybe, in the near future, I think we need to do more works on the confirmation of these states. And okay, let's move to the Y states. I think I will start with Y4260. This is observed in the initial radiations by the Baba. So most recently, actually, BESS3 measured the cross sections using the energy scan data. We can see there is a clear shoulder just around 4.3 GeV. And if we fit this structure with two components, we found that one is around 4.2 and the other is about 4.36 GeV. So most recently, the D0 also measured the mass, provided the mass spectrum of gypsy pi. We can see also there is clear structure just around 4.2 GeV. And actually, BESS3 also performed the measurements of the cross sections for different processes, including the pi psi primes, pi h sum c, and for other, omega chi c0. So we can see that the line shapes from this different process are really different from that of the pi gypsy, but both the states of the 4220 and the 4360 are clear. But of course, we can see that the static uncertainty is quite large. Maybe in the future, with more data, we can provide the more precision measurement. And because we observed the structure in the pi pi j psi, then how about the structures at the pi pi psi prime? So actually, this is a plot from the both Baba and Bell. We can see besides Y4360, there is another structure just around is 4660. Because this structure is quite close to the lambda pair mass threshold, so Bell also performed the analysis for using the ISR process for the lambda pairs. We can see there is a clear enhancement just close to the mass threshold. But most recently, Bell performed the analysis for the B decays to the K lambda pairs, but no evident peaks was observed, but we can see the status is still quite low. In the future, I think Bell 2 maybe could do more works on this decay. And okay, let's move to the Z states. I think it's well known that two ZBs were observed in the pi pi Wolfsino and pi pi H sub B. So both of them, we know that the spin parity favors 1 plus, and we know that for this one just close to the B star, and this one close to the B star mass threshold. And so Bell performed the analysis, so we can see that really we observed the enhancement at the B star and the B star. So for the decays of these two ZBs, we can see both this strongly coupling to the B star and this one strongly coupling to the B star. And so theoretically, this thinks that both of them may be the evidence of the molecule. And of course, we have two ZBs. So how about the ZB-like states in harmonium states? And about 5 years ago, both Bess3 and Bell observed the ZC1300. After that, Bess3 performed a serious study on the ZC states, and so far we know that this ZC for the 1300 have a spin parity of 1 plus, and we also know that two isospin triplets established. So most recently, also the D0 present the observation of the ZC 1300. So we have observed the structure for the pi J side and how about the pi psi prime. Actually, Bess3, for the first, Bell presented the evidence of the structure of the pi psi prime, and Bess3 analyzed the energy scan data and observed the clear structures. Using simultaneous feed, we observed the mass, and with a reasonable increment with the Bell is the result. And the most interesting is the ZC4043, which is observed at Bell, and recently LGCB performed the amplitude analysis, and the mass and the width are also consistent with the Bell's results. And let's move to the PC states. We know that the pentaquark search is also, we have performed search for a long time, but until 2015, LHCb observed a very narrow peak in the gypside proton mass spectrum, and using the amplitude analysis indicates that besides this narrow peak structure, we also need another a little bit broader one to describe the data. And also LHCb performed the analysis for the lambda B to the gypside proton pion, and this is a chemical surprise process, and but we can see there are some structures. The amplitude analysis indicates that the total significance of these PC states is just now around 3 sigma. But in these states, we cannot ignore the contribution from the ZC states. But so far, I think the statics for these decays, also for these decays are still low. I think in the future, maybe LGCB could do more work on these decays. Actually, to test the nature of the PC states, LGCB also performed the other analysis for the 11B to the Chi-C, proton K, and the CB decays. Because theoretically, if the PC states are from the kinematic effects, it should be absent in the Chi-CG proton K. But we just observed these decays, but statics is too low to do the amplitude analysis. I think in the future, LGCB, besides the PC, will also maybe look for the string hidden charm pentaquarks. So this is the current picture for the charmonium spectrum. We know that there are many of them are out of the quark model. So what are these exotic hadrons? So there are many theoretical interpretations on these exotic hadrons, including the multi-quark states, hybrids, and hadron charmonium, and so on. But none of them so far could offer us a whole picture for the observed exotic states. So I would like to give a short summary. So now it's a new era for the hadron spectroscopy. In the last decades, we observed many exotic candidates. And we also have many theoretical models, but so far, I think none of them could offer a clear picture for these observed hadrons. So at present, there are still many experiments, including BES3, BEL2, and LGCB, still pay much attention to these exotic searches. So I think more results could be expected from these experiments. But here I just stolen slides from the Professor Steve Olsen, president at the CHAM 2018. I think, just after the 16 years discovery of the Keon, we have the quark model. This is a breaking through in understanding of the hadrons. And the X3872 just discovered about 16 years ago. So now it's time for us to have a new idea to talk about this exact hadron. So here I just would like to say that besides the experimental efforts, I think for theoretical calculus, maybe your time is also coming. Thank you very much.
Thanks, Dr. Pang. So this is the really nice, nice summary of the many impressive experimental results on the hadronic exotic. So now switching gear a little bit to the heavy ion physics program. Next speaker is Ralph Elbeck, and he will talk about the experimental aspect of the heavy ion physics program.
Yeah, good morning. It is my pleasure to be here and to have the opportunity to discuss with you some features of heavy ion physics, which is the many body physics of high energy density QCD. And in this context, the most relevant properties of QCD are the confinement of quarks and gluons into hadrons, which at a large Q square actually the interaction strength goes down, turning into asymptotic freedom, and that gives actually rise to a very feature-rich phase diagram of strongly interacting matter, where the hadronic world around us turns into a world which is dominated by platonic degrees of freedom if one goes to very high temperatures and or high net baryon density or baryochemical potential. This is explored, this phase diagram, at many facilities with many experiments looking at a large variety of observables, and I cannot discuss all of them. in the limited time. So I have chosen to focus on the region of highest temperatures and vanishing baryochemical potential that one can study in the laboratory at the LHC, where lattice QCD tells us that at a temperature of around 156 MeV, the hadronic world turns into a platonic world with a rapid crossover. A heavy ion collision at ultra-relativistic energies is a complex process. A large energy is deposited in a small volume, creating high density in the initial stage. By hard scattering processes, the system then equilibrates and expands and cools down, and eventually goes through the phase transition again, forms hadrons, and the final state particles propagate through the detectors. And we want to study about the early QGP phase, learn something about this from the measured final state particles, and that means we need a reference system in which no QGP, no quark-gluon plasma is produced. And the traditional approach is to use proton-proton collision as sort of a vacuum baseline and study proton-nucleus collisions to investigate cold nuclear meta effects due to the presence of the nucleus in the initial stage. So at the LHC, such a program is conducted with proton-proton, proton-proton, and lead-lead collisions. And I would also like to point out a running campaign of only 6 hours in 2017 with xenon nuclei, which is quite interesting, because if you look at the different sizes of the xenon and lead nuclei, a central xenon-xenon collision and the semi-central lead-lead collisions have about the same volume, but they have a very different initial geometry. One question that will run through the whole presentation is the one whether these small systems that traditionally we have looked at baselines actually are baselines, or whether there's more to them. I will start with soft probes, meaning the production of light flavor hadrons at low PT, which allow us to characterize the bulk of the medium. And as I said already, one question is whether we have also bulk medium production in small systems. Looking first at the sheer number of particles that is produced in such collisions, what is shown here is the number of charged particles per unit pseudo-rapidity density per participating nucleons as function of collision energy, where you see that for nucleus-nucleus collisions per participant nucleon, more charged particles are produced than in the small systems. And if you look at the total number of charged particles that you have in a central collisions, a head-on-head collision of nuclei, then in lead-lead at 5 TeV, we see a bit more than 20,000 charged particles, and in the smaller xenon-xenon system, still about 13,000. So we create of order 10,000 hadrons in local thermal equilibrium. Now, if we look at the transverse momentum spectra of these hadrons, we get a first glimpse at collective phenomena. What's shown here is pion spectra and proton spectra from peripheral collisions going up to central collisions. And what you see is that even at the LHC, about 95% of all the particles that are produced are soft, so are in the range below 2 GeV in transverse momentum. And what you also see in these textbook quality momentum spectra, you see that going from peripheral to central spectrum, the maximum of the particle yield moves actually to higher momentum, which is indicative of a hydrodynamic expansion of the system, an explosive radial flow of the system that is developing, which becomes more violent with centrality and which also grows with particle mass. So you see this more pronounced for the protons than for the pions, which is characteristic for a source that is radially expanding with a constant velocity. And velocities in this expansion of about 2/3 of the velocity of light are reached. Another way to look at collective expansion of this source is to look at azimuthal distributions. If you look at in the classical picture at the collision zone that is formed, then you see that this is spatially anisotropic, so it has this almond shape form. And due to scattering of the partons in this medium, pressure gradients develop that lead in the end to an anisotropy in the momentum space, and this is analyzed typically in the Fourier expansion of the particle distributions versus the azimuthal angle, and these Fourier coefficients characterize this azimuthal anisotropy, and the one that is characteristic for this elliptical motion is called V2, called also elliptic flow. Of course, a nucleus is not a homogeneous sphere, but it consists out of nucleons, which gives rise to a lumpy, well, sorry, that was too fast, which gives rise to a lumpiness in the form, in the shape of the initial system. And this is then subject to fluctuations. And not only this naive elliptical shape turns up, but there are also higher harmonics that one has to take into account. So the V2 is sort of a measure for the initial geometry, and the higher harmonics are more affected by fluctuations. Now, if one looks at these harmonic parameters, these Vn, as function of collision centrality, going from central to peripheral collisions, then what you see is that the V2 values, which indicate the initial geometry, are dominant for the semicentral and the peripheral collisions, while when you go to the central collisions, the values of the higher harmonics become similar to the values of V2. That shows you that initial fluctuations are actually becoming very important. Another way to look at collective effects and at V2 is to look at long-range correlations in delta phi and delta eta. So this is a two-particle correlation. Here's the difference in azimuthal angle. Here the difference in pseudo-rapidity. This is for p-lead collisions with rather large multiplicity of charged particles. And you see here the delta eta, delta phi equals to 0. You see a jet peak and a wayside structure also due to the back-to-back jet production. But what you also see is that there is a long-range correlation for small relative angles in azimuth and large separation in eta, which is actually reminiscent of elliptic flow. And we see this structure called a ridge in high multiplicity p-lead and also in pp collisions. So if you take these correlations and extract the elliptic flow V2 from those, then you see in lead-lead collisions, in p-lead collisions, and also in pp collisions, you see a positive V2 in all three systems. So we see in the small systems features that are similar to those that in nucleus-nucleus collisions are interpreted as a consequence of collective flow. Another way to look at this is shown here. This is the V2, the elliptic flow parameter, as function of charged particle multiplicity for a variety of systems, nucleus-nucleus collisions, lead and xenon. And here you have the V2 values for the small systems. This has been done, this analysis. I should mention that there are various techniques how to extract these V2 coefficients that have a different sensitivity to non-flow contributions. So of course one does not want to have effects due to jet correlations spoil an observable that is supposed to tell something about collective behavior. And we see here that even in the small systems we see collective, at least we see positive V2 that one might want to interpret in the sense of collective behavior. If we now look at p-lead collisions a bit more closer, we can use the fact that, for example, in the Alice experiment, one can identify different particle species. And what's shown here is now V2 for different particle species as function of momentum. We see a clear mass ordering versus transverse momentum, which is consistent with an hydrodynamic expansion. And we see a grouping of the baryons and the meson at intermediate PT, which is also observed in nucleus-nucleus collisions. One can switch off the flow, so there are systems in which no collective effects are observed. Here's an analysis of Aleph archive data, the plus and minus collisions at 91 GeV. You see here there's two particle correlations, and if you look at the region where in small systems the ridge is observed, you see no deviation from Pythia, so there's no evidence for any long-range correlations in this system. And also in deep inelastic scattering data, EP from Zeus at Hera, one sees the same feature. In blue is two particle correlations close in eta, where one sees at low particle multiplicity there is a correlation. That's essentially this jet peak. But if you look for large differences in pseudo-rapidity, there is no signal seen for any flow correlations whatsoever. So apparently one needs multiple partonic interactions to set up an initial geometry that can create flow. Now we can turn to yields. Light flavor hadron yields in central lead-lead collisions are shown here. From the lightest particles, pions, to baryons. Here we have the protons, the lambda, multi-strange baryons, and even nuclei and and anti-hypernuclei. The freeze-out temperature, they are compared here with predictions from hydrochemical thermal equilibrium models, which can describe these yields with temperature close to the transition temperature. There are a few tensions here, in particular for these strange resonances and for baryons at the few sigma level, which we have to study in more detail and which might give us access to the hadronic final state. Matter and antimatter is produced in equal amounts, and this thermal model even works for objects such as anti-hypernuclei, which are bound only by about 100 keV in a medium that is much hotter. So ultra-relativistic nucleus-nucleus collisions are sort of a factory for anti-hypernuclei, and this has impact even beyond heavy ion physics. So we have looked at anti-hypertriton production, so this is the proton-neutron lambda bound state, which we can reconstruct in the helium-pion decay, and we have measured the lifetime of the anti-hypertriton, which is shown here together with previous measurements and compared to the free lambda lifetime. It's not well known as you see, and we can constrain this value, which is important for the nuclear physics because this lifetime is sensitive to the hypernucleon interaction potential. Also, the anti-nuclei production has implications. The yield and spectra that we measured can be used as input for model calculations that can help to estimate the background in the search for anti-nuclei of galactic and dark matter origin, and this is indicated here. So this is the Poisson probability for detecting 1, 2, 3, 4 anti-helium-3 nuclei in a 5-year measurement campaign with AMSO2 to look for antimatter from galactic origin. Strangeness production in small systems is the last bulk observable I want to look at. What's shown here is the ratio of protons, kaons, and then the phi meson, and then strange baryons, 2 pion yields, shown as function of multiplicity for various systems, and we see a smooth transition from large to small systems, which might point as a common origin of baryon production here. This is a challenge for conventional, sorry, that was too fast. A challenge for conventional PP event generators, for example, Pythia, just citing Torpion Thürstron from the recent Quark Matter conference. In particular, this multi-strange baryon production requires new mechanisms, so this could open a new field of study in that branch. Now I turn to hard probes, the hard PT hadrons on jets, which are produced early on in the collision and are calculable by PQCD at high PT. We look first at the nuclear modification factor, which is the yield of charged hadrons or particles produced in AA collisions divided by the yield in PP collisions times the number of binary collisions to take care of the geometry. which is 1 if there are no nuclear effects and deviates from 1. In particular, is larger than 1, is smaller than 1 if in medium energy loss is important. What's shown here is the RAA, the nuclear modification factor of charged hadrons in lead and xenon. Xenon collisions, we see a suppression of about a factor 2 in the range between 5 and 10 GeV, and going then to peripheral collision, the suppression becomes smaller. And what is interesting to see is that the suppression scales with the number of participants or with the number of charged particles being produced. This is RAA for xenon and for lead in 2 different momentum bins, and they agree with each other nicely. Here's the PT dependence for 2 centrality classes in xenon and lead collisions with the same multiplicity of charged particles. Now the inevitable question is what happens in small systems. So this is the nuclear modification factor in p-lead collisions. Here you have it in nucleus-nucleus collisions. There is no energy loss in the small systems, and this one can also understand because to have energy loss one needs some path lengths, and in small systems the path lengths can be short. Turning to open heavy flavor, so the production of hadrons with charm or beauty quarks. They're produced like hard probes because the quark masses are large, but at low PT they interact like soft probes, which makes them very interesting. The nuclear modification factor is shown here for d mesons as function of PT. We see the suppression, and we also see flow of d mesons in nucleus-nucleus collisions, and the combined observation of energy loss and flow helps to constrain model parameters and helps to extract transport properties from the data to model comparison. The same is true for beauty. Also, beauty yields are suppressed. This is seen here for B mesons in various channels compared to the prompt D meson. We also see this in semi-leptonic decays, and it turns out that also beauty shows a positive V2, and so we can have a higher sensitivity test of heavy flavor transport here. In small systems, you will not be surprised to see that we do not see energy loss of heavy flavor. We measure RP-LED here also as function of rapidity, where we can start to constrain gluon and PDFs. And we see a positive V2 of D mesons in the small systems, not as large as for the other non-heavy flavor particles. The charm baryons are also very interesting. If we look at the ratio of lambda C to D0, then we see this ratio being larger than what we have in Monte Carlo generators, and we see that the ratio, that the baryon to meson ratio is actually very similar. Also in light systems here, shows similar features than the same baryon to meson ratio in the strange and in the light sector. In lead collisions, we see an even larger ratio of lambda C to D0, and this poses the question whether we understand charm hadronization and the role of coalescence actually. Finally, I turn to quarkonia, which in the medium should be suppressed because of the bi-screening in the colored medium. Competing mechanism, of course, is that if we have a system which has a large number of charm quarks around, then at the phase boundary, they could form new quarkonia by coalescence, essentially. And this is seen for the J-psi. Here's in nucleus-nucleus collisions. The J-psi RAA is function of centrality for measurements here at the LHC compared to measurements at RIC. And you see a reduced suppression at the LHC, even though the energy densities that are reached should be higher. That speaks in favor of an additional production mechanism, which could be the regeneration of the J-psi at the phase boundary, which is also supported by this measurement here, which shows the rapidity dependence. So at mid rapidity, at low PT, we see an enhancement, and that is where we have most of the charm quarks available. In addition, if that's the case, then the J-psi should also pick up flow from the flowing charm quarks, and it does. But what comes back to the rescue of sequential dissociation, if we look now at Bottomonia production, CMS has measured Y1s, 2s, 3s in PP collisions shown here. And this in red here is what one would expect in lead-lead collisions if Bottomonia are not suppressed. And obviously, if you compare them to the data, there is a very clear suppression pattern. Shown here is now the nuclear modification factor as function of the number of participants from peripheral to central collisions for Y1s, 2s, and 3s in comparison with model calculations, which then allow to estimate, of course, model dependently, the initial temperature that is consistent with this observed suppression pattern. And what is concluded is that the initial temperatures at the LHC are way beyond the phase transition temperature of about 150 MeV. That brings me to my brief summary. In ultra-relativistic heavy ion physics, we have seen a lot of progress in the last years and a wealth of new results from the LHC. Whoops, that was too fast. As well as from lower energies and from the fixed target program at CERN. The data analysis is in full swing. We have seen probably a crack in the traditional paradigm that in PP and PLED or in small systems, no medium, no collective effects are relevant, at least at high multiplicities. And for the future at the LHC, in run 3 and 4 at the LHC, we will see unprecedented collision rates, 50 kilohertz lead-lead collisions, which will improve, of course, the measurement of rare probes. This goes hand in hand with major detector upgrades in order to cope with these increased rates, which will, I think, we will open a new era for ultra-relativistic heavy ion physics at the high energy frontier, and at the high net baryon density frontier. We are looking forward to new facilities, NICA and FAIR, that will come up in the not too far future. Thank you.
Thanks, Dr. Haberbeck. So thanks also for giving us the very nice comprehensive reviews on the experimental aspect of the heavy ion physics program. So now, time for questions.
Good morning. Thank you for the very nice talk. You already mentioned that with a sort of high increased statistics that we will get with 1.3 and 1.4
Yes.
for the heavy ion collisions at the LHC, that rare probes is one of the things, yeah, as you say, they're rare, that of course that is something where you can improve. But could you give maybe a bit more deep overview, are we really going to learn now with the additional statistics?
Yeah.
Can we go to higher order coefficients maybe of the radial flow, or maybe we can get
there's
top quark flow, or what?
Well, maybe not top quark flow, but there's a number of observables that will be improved. Those observables that I have shown here, for example, not only multi-strange but also multi-charm baryons, for example. So one can extend those studies in that sector. One can do high-quality measurements, for example, of dileptons, low-mass dileptons, to look for signatures of the chiral phase transition as well. One can do studies of nuclei and loosely bound objects with much better precision and statistics. One can go, and for the heavy flavor physics, it is really crucial to go to low PT, to 0 PT, where we suffer experimentally from really small signal to background ratios. And this is, to cure that, what is needed is high statistics and high precision to resolve the displaced decay vertices. And these are things that are addressed also by, not only by statistics is of course addressed by the increased interaction rates at the LHC, but the precision is also addressed by corresponding upgrades of the detectors.
Right. Steve?
Yeah, thank you very much. That's a very complete answer.
You showed very impressive signals for charmonium and bottomonium and collective effects. it would be very interesting if you could study the same properties of some of these new particles we are seeing that might be molecules or
Yes.
tetraquarks. Are there any, but then you have to combine a J psi with 2 pions or something. Is there any possibility for that?
Not with the data that we have right now. This might become a possibility in the runs 3 and 4, actually. But with the data we have at the moment, there is essentially no chance.
All right, so if there is no further questions, we can move on to the next talk.
Thank you.
Thanks, speakers. Next speaker is the Tatsumi Hirana. He will tell us about the theoretical aspect of the heavy ion physics program.
Okay, so thank you very much. So it's my great pleasure to be here. So as a usual disclaimer, I would say that it is very hard to deliver a proper overview within 20 plus 5 minutes. So the topics covered in this talk are highly biased. So I apologize for that. So this is the outline of my presentations. So after a brief introductions, I will pick up 3 topics. The first one is anisotropic flow. The second one is jet modifications. The last one is small colliding systems. So finally, I will summarize my presentation. Okay. So, wow. What is shown here, What is shown here is that the conjectured phase diagram of the QCD. The horizontal axis is the chemical potential for baryons. The vertical axis is the temperature. So you know that if the temperature is low and also the chemical potential is low, the quarks and gluons are confined into hadrons. However, if the temperature is sufficiently high, quarks and gluons are freed from hadrons. So this is called quark-gluon plasma. The physics of the quark-gluon plasma is the condensed matter physics of the elementary particles. The goal of this physics is to investigate the quark-gluon plasma as a chiral symmetric matter, structure of vacuum, the order of phase transition between these two, and finding the location of the critical point and the first order phase transition line here, and the equation of state, especially with finite baryon chemical potential, transport coefficient, and so on. Okay, so this is the recent lattice QCD result for the equation of state. So what is shown here is that the pressure as a function of temperature in the low temperature region and the high temperature regions. So you see that the pressure rapidly increases with temperature around 200 MeV. So, however, if you look at carefully in the low temperature region here, so you don't see any sign of the phase transition between the hadrons and the quark-gluon plasma. So in this sense, the crossover behavior appears between the hadrons and the QGP. So anyway, so this is the first principle calculations, so which are available at least at the vanishing baryon chemical potentials. Okay. So in order to investigate the matter under such extreme conditions, so we can utilize the high energy nuclear collisions, so Large Hadron Collider in CERN and the relativistic heavy ion collider at Brookhaven National Laboratory. Okay? So these are the unique approach to create matter under extreme conditions on the Earth. Okay? So, okay, so these are the 3 major findings of the QGP properties. The first one is that the QGP is smoothly flowing. So here, kinematic viscosity, so which is the ratio of the shear viscosity to the entropy density, is of the order of 0.1. So like this. So here, this value can be compared with the other materials, such as ultra-cold atoms, heliums, and water. So you see that the kinematic viscosity for the quark-gluon plasma is the smallest around here, so which can be comparable with the conjectured smallest value from the string theory. The second one is that the strong drag against propagating jet. So for 100 to 200 GeV jet, the 10 to 15% of the energy is lost on average in central heavy ion events. So what is shown here is that the Lego plot. So the leading jet has 200 GeV. However, the sub-leading jet has only 70 GeV. So apparently, the energy is not balanced between these two jets. Okay? The third one is that the QGP is extremely hot. So temperature is roughly 400 MeV, so which is equivalent to the 5 times 10 to the 12 Kelvin. So this was shown in the Guinness World Record. Okay? So to obtain these kinds of information about the Cold-Gluon plasma, so we do some bottom-up approach. So this is quite similar to the situation in the observational cosmology. So in this case, the analysis tools play a crucial role to obtain, for example, the cosmological parameter and some information about the early universe. So here in the heavy ion phenomenology, so we need to develop a dynamical model to describe the space-time evolution of the nuclear reactions. So then, by analyzing the experimental data, so one can obtain the physics properties of the Cold-Gluon plasma. Okay. So this is the analysis tool, or dynamical modeling in high-energy nuclear collisions. So what is shown here is that the schematic view of the space-time evolution of high-energy nuclear reactions, starting from the colliding energetic two nuclei to the free-streaming hadron gas. In the intermediate stage, so we expect that the Cold-Gluon plasma fluid is created like this. So we can divide the energy scale into the hard sector and the soft sectors. So in the hard sectors, so this is quite similar to the jet physics in PP collisions. So starting from the perturbative QCD to create the jet, and finally the jet fragment into hadrons. However, the main difference between the PP collision and the nucleus-nucleus collision is that the produced jet has to travel through the Cold-Gluon plasma fluid like this. So there must be some interaction between the jet and the QGP fluid. Okay? So jet would be modified. Okay? So we need to describe this kind of process by using the hydrodynamics plus jet models. So in addition to the dynamics of the jet, so we also need to describe the space-time evolution of the Cold-Gluon plasma, okay, in the soft sector. So this is a kind of the dynamical modeling in high-energy nuclear reactions. Okay? So by using this dynamical model, so we analyze the three observables. The first one is the anisotropic flow. Okay? So what is shown here, okay, by the way, so anisotropic flow is the response to the initial fluctuations of the geometry. So what is shown here is that the entropy density distribution in the transverse plane perpendicular to the collision axis. So you see that the colliding two nuclei here and also here. The overlap region becomes the Cold-Gluon plasma. So you see some hotspot here or here. So here, this QGP has an elliptic shape, something like this. So due to the anisotropic pressure gradient, the system expands mainly this directions rather than this directions. So this is called elliptic flow. But if you look at the shape, something like this, so you see some triangle shape here. So in this case, the system would expand something like this. So this is triangular flow. And you also see some rectangular flow, something like this. So the system also responds to this kind of shape, so which is called quadrangular flow here. Okay? But anyway, so we can Fourier decompose the azimuthal angle distribution to obtain the Fourier coefficients. So these Fourier coefficients contain rich information about the system. Okay, so here this is the Fourier coefficient for the second order, third order, and the fourth order as a function of the transverse momentum in central collision, mid-central collisions, and peripheral collisions. So these are the results for pions. Okay? The Fourier coefficient are sensitive to the initial profile of the quark-gluon plasma, the equation of state, transport coefficients, and the degree of equilibration. So the anisotropy has a strong power to constrain the details of the dynamical modeling. So here the Alice data are compared with some dynamical model result here. So one can extract some information about the properties of the quark-gluon plasma like this. So here, these are the results from the Bayesian analysis. So left figure shows the sound velocity square as a function of temperatures. So left panel shows the unconstrained parameter set of the sound velocity square as a function of temperature. So but the experimental data gives us the posterior probability of parameter, which is shown in the right panel. So through the Bayesian analysis. So what is interesting here is that this posterior probability of parameter is consistent with the result from the lattice QCD. Okay? So now we can say that the experimental data meets the first principle results for the first time. Okay? So right figure shows the transport coefficients constrained from the experimental data through the Bayesian analysis. So here the left panel shows the shear viscosity, the right panel shows the bulk viscosity. So here, my message is that the physics of the quark-gluon plasma is getting changed from the discovery stage to the precision stage. Okay, now let me move on to the jet modification. Okay, so this is again the Lego plot of the dijet asymmetric event. So here, the leading jet has 200 GeV, and the sub-leading jet has only 70 GeV. So you might think that, this is a missing PT, so there must exist some new particles here. But here in heavy ion collisions, so this is called jet quenching phenomenon. Okay? So energy of the order of 200 GeV jet is dragged by the medium with temperature 300 MeV just in a few femtometer. So right figure shows the schematic view of the jet quenching phenomenon. So just after the collisions, the quark-gluon plasma is created. But in addition to that, the dijet is also created here. So one jet can escape from the medium immediately like this. However, the other jet has to travel through the quark-gluon plasma like this by radiating the gluons. So then finally, this jet is quenched. Okay? The question here is that where the lost energy goes. Okay? So if you look at the azimuthal angle distribution of the transverse momentum, so here this is the leading jet part, so this is the sub-leading jet part. So apparently, the energy is not balanced between these two. So however, energy and momentum are balanced by soft particles at large angle from the jet axis. So if you look at here or here, so you can see the soft particles. So here, the yellow color corresponds to the transverse momentum from 1 to 4 GeV. So actually, the energy is balanced if you take into account these soft particles. So how can we describe this kind of phenomenon? Okay? So we solve the hydrodynamic equations with the dynamics of the propagation of jets. So here, dijets are propagating along the y-axis here on the top of the QGP expansion. Okay? So you see here and here, so these are the Mahcon structure. Okay? So these come from the deposited energy from jet. Okay? So one can analyze the jet structure function like this. So these are the experimental data obtained by the CMS collaborations. So in the small r region, the structure can be described by the event generator PCR. However, the PCR result is deviated from the experimental data in the large angle region. However, so if you add the contribution from the deposited energy from jet, you can fill the gap between these two. So you see that the jet structure function is described by taking into account the Mach structure of the jet. So here, this is a new channel to constrain the transport properties of the core-gluon plasma. Okay, so in the last topic, I would like to discuss about the small colliding systems. So high multiplicity PP event. So maybe you might think that this is a garbage dump for the beyond standard model particles. So this is a sort of finding a needle in a haystack. So however, as a heavy ion physicist, so this is a treasure trove. The question is that to be QGP or not to be. So that is the question here. Okay? So this is the particle ratio to the charged pion as a function of multiplicity at mid rapidity in lead-lead collision, the proton-proton collision, proton-lead collision, xenon-xenon collisions, and lead-lead collisions. From top to bottom, the proton, k-short, lambda, phi, cascades, and omegas. So you see that all results for each hadron lie in a single curve. Okay? So regardless of the geometry, system size, or collision energies. So this means that the ratio of the particles to the charged pion scales with the multiplicity. So if you look at these, the bottom two, the increase of the multi-strange hadrons is more rapidly. So I think that this is one of the important experimental data in small colliding system here. So let me blow up the result in the multi-strange hadron case. Okay? So here, in the case of the cascade, the particle ratio can be described by the string fragmentation model. So here, for example, the PCR calculations. So here, the control parameter is the string tension kappa. Okay? So this is only the parameter to control the particle ratio between the multi-strange hadrons and the charged pions. However, the experimental data increases with the multiplicity, so eventually saturate above the DND eta 100. Okay? So above that, this ratio can be also explained by assuming the chemical equilibrium for the produced matter. Okay? So here the control parameter is the chemical freeze-out temperature here. Okay? The question here is that how can we deal with both string fragmentation and emission from chemically equilibrated matter at once? Okay? So core corona picture enables us to describe this kind of monotonic increase of the particle ratio. Okay? So in the case of the low multiplicities, the produced partons are just fragment into hadrons like a conventional string fragmentation model. But if as the multiplicity is getting high, some dense region becomes the chemically equilibrated matter, so which is nothing but the core-gluon plasma fluid. So now the multiplicity is sufficiently high. The system is dominated by the core part like this. Okay? By taking into account this kind of picture in the dynamical model, so one can reproduce the experimental data of the particle ratio, something like this. So what is shown here is that the ratio of the cascade to the charged pion as a function of multiplicities. The open symbols are obtained by the Alice collaborations. The closed symbol are the result from the core corona picture. Okay? So you see that this monotonic increase and the saturating behavior reproduced by using this model. So here the low multiplicity limit, the string fragmentation can be used to explain the experimental data. However, in the high multiplicity limit, so the hadron productions are from the QGP fluid. Okay? So now the key number is that the DND eta is around 100. So above that, the QGP formation is dominated in the system. However, below 100, the QGP is partly created even in small colliding systems such as PP or P-red collisions. Okay? So this is quite important interpretation even in the small colliding systems. Okay? So let me summarize my presentation. Oops. Okay. So beyond the findings of the QGP is smoothly flowing, strong drag against propagating jets, and the QGP is extremely hot, the physics of the QGP gets changed from the discovery stage to the precision stage, as you see as the Bayesian analysis. Okay? So analysis tools or dynamical models play a crucial role in extracting physics property of the core-gluon plasma. So in this conference, some of you are interested in the high multiplicity PP events. So actually, the high multiplicity small colliding systems are new trends. Okay? So here, the key number is that the DND eta is around 100, so regardless of the system size or collision energies. So below that, so we need to think about the creation of the core-gluon plasma. So now I think that the high energy physics community and the heavy ion collision community should meet together to attack this non-perturbative problem of the QCD. Okay, that's all. Thank you.
Okay, thanks, Dr. Hirana, for summarizing the heavy ion theory nicely. So, the time for a few questions.
That was a very nice talk. Thank you. So you talked about how the strangeness enhancement is independent of root S. But at some point, you have to go down low enough that the strangeness enhancement will go away. So at LHC energies, it really doesn't matter. But at what root S does it disappear if you go low enough? Okay.
So actually, within these collision energies, it seems that the strangeness enhancement doesn't depend on the collision energy. So like this. So here, this is PP collision at square root S is 7 TeV. So this is 5 TeV. So this is 13 TeV. So of course, in this case, we assume that the chemical equilibrium. So however, so if the collision energy is getting lower, so we might not expect this kind of chemical equilibrium. In that case, maybe this kind of scaling breaks down.
Do you have a sense of what kind of root S that might set in at?
Okay, so actually I have no number at the moment, but there are some recent results from the star collaborations at REAK. So actually, at least at REAK energies, this ratio is just on the top of each other. So, but I don't have the exact number for the breaking of this ratio.
Thank you.
Yeah, it's just a comment on this question. Strangeness enhancement, of course, was discovered at the SPS at CERN for lambdas, size, and omegas. So we know it is there at root S of 15, 20 GeV. Of course, experiments have been done even at lower energies. At CERN, we have tried to push down to 40 GeV. That was momentum, and that's about 8 GeV root S, and the effect still seems to be there. Measurements at yet lower energies, say at the AGS, are inconclusive because the cross sections for these particles are very, very low.
Okay, so thank you very much for that comment. So I also would like to see those experimental data in the lower energy as a function of the DN data, not the, for example, N part. But anyway, thank you for that comment.
All right, so if there is no further questions, so let's thanks again to Dr. Pirano and also all speakers in the morning. So.